This is Chelsea Sizemore, Lab M07. Lab 1, Constant Velocity Motion. I made an observation of a video of my friend moving her hand across the screen. I modeled it, the main result applying the momentum principle or Newton's second law, by setting Fnet equal to 0 to model good predictions of the observed motion. Here is the clip of my friend moving her hand. I used the first frame to set the origin at the tip of my friend's thumb. I chose the x-axis and oriented it so that her hand would move in the positive x direction at a constant velocity. I took the center of her hand as the average position and marked it, as shown on the screen. I used the diameter of her hand by using the calibration stick, set that as a length scale of the video, which I set as 0.1016 meters. The time length for the frame is about 1/30th of a second. The total clip time is around 1 second. The last frame was before her hand is completely stopped. To predict the motion, I needed the mass of her hand, which I took to be 0.45 kilograms. I used the initial position of the ball, which I got from the analysis of the first frame of the video. The average velocity I estimated by taking delta x over the entire video clip. That is the final position minus the initial position, and divided that by the total time of the video clip, which is about 1 second. That gave me the estimate of the initial velocity. Lastly, I chose delta t to be small compared to the 1 second time elapsed of 0.01 seconds. So I predicted for starting at time for about 2 seconds and applied Newton's second law, so the final velocity and constant velocity will be equal to the initial velocity, which means the second term, Fnet over m delta t, has to be equal to 0. The only way for that to happen is to have Fnet equal to 0. I set Fnet equal to 0 in the model and then used that to predict the motion based on the given initial condition and system mass. Notice that the system mass doesn't come into play because if the Fnet is 0, then the mass does not matter. The visualization, here's a visualization of her hand. The origin is here, which the ball we are going to consider as a hand goes to the right, and the graph shows that. It starts at the origin, going from the positive x and continues to get more positive. The best way to compare the model and the experiment is to plot both the data and the predictions on the same graph. So this is the x position versus time. X is in meters, time is in seconds. The blue represents the experiment, the black line represents the model. The model line tracks the line of blue diamonds, so we can call this a good agreement between the model and the experiment. For the what if question, what if I made the choice of origin in a different place? How would my results change? What if I chose the hand going to the right in the negative x direction? So in the model, the only changes would be the hand position and the hand velocity would change to the negative. The ball's motion should look the same. The ball should be still moving in the right direction, but the graph should look different. The graph goes in the negative direction and continues to go in the negative direction as time advances. However, in this screen, it doesn't, but it should. It's going in the negative direction, but instead it's going to the left. Instead, the ball should be still going to the right in the negative direction. Finally, what does it mean to start with the V constant we found? What does it mean? We start with the V constant we found by setting Fnet equal to 0, which are the total pushes and pulls are 0, we got a good fit. This results that if Fnet is not 0, then the velocity would not be constant. That is, the object would speed up or slow down or change directions. In the model, the only thing that should change would be the Fnet. The Fnet would not be 0. Instead, it has numbers. Here's the model showing the change in direction and velocity.